Well, looks like we made it, folks. Welcome back to class. We're finishing off week 7 today. And also, we're in a really great moment of the course. We're about to finish off our entire section on chapter on logic. And from there, we're going to go into the section on, rather, chapter on proofs, where we're going to apply the techniques that we learned. I wrote here to write very, very convincing arguments. Think of the arguments we're about to write here, we're calling them proofs, but you could say these are just really convincing arguments considered airtight that could convince just about anyone who can follow along with the notation you write, the mathematical rigor you put into there, exactly how the work goes, and then themselves be very convinced on what you're trying to show. So we're running through the course. This is one of their bigger sections. This one I want to go slow on because it really connects a lot of material. It's going to connect a lot of stuff from this section, for example. The logical equivalences, the tautologies, De Morgan's laws, all that kind of stuff works its way back into section 4.3. But in a way that's good. It means we didn't do all of this all for nothing. We're going to apply it right away once we move into the next chapter. But any questions at the moment, folks, before we get started? Okay, let's get started then. So now back to section 3.3, or excuse me, 3.5. Here's where we left off, a pretty big application. And I find that this question is really pretty tricky in my opinion. So for the people who are more coding minded in this class, please don't hesitate to chime in on how this one goes here with suggestions or modifications. But first, part A is kind of the standard problem right here. We have a lot of information, and we're just trying to express this statement using quantifiers. So let's begin with the context on this. Just to make it feel more engaging, imagine you've been hired on as a high-level technical administrator at ISU. I don't know if that's a real job position, but let's imagine it is. You're going to be working in a lot of databases, answering questions from other parts of the leadership at ISU. And so a lot of your work is going to be dealing with this kind of stuff right here. So to get started, we have a set S that's going to be the set of all students at ISU. The registrar would definitely have a database containing that information. And we're defining a new set. That set C is going to be the set of all courses offered at ISU. And then finally, we have a predicate. T of the input XY is the statement student X has taken course Y. It's a real mathematical function in the sense that this function, txy, goes from, well, x comes from the set of students. So the domain of this is going to be S. Well, there's more to it, right? Y came from the set of courses. The domain is a cross product, S cross C. And then it maps into the Booleans because it's a predicate function. All its output is going to be is true or false. So there's our mathematical function. And just for the sake of kind of tying this all together, let's color code S, the set of all students, blue, C, the set of all courses, green. And finally, in part A, we're going to express the statement. It may or be true or may be false, but the statement says every student has taken at least one course. Interesting statement. I would say it's false because you might think to yourself, well, what about freshman students? They are taking classes, but they haven't taken or completed a course. There's a lot to say here to try to make it a lot more precise. But working with just this statement right here, let's quantify it using the sets above S and C, as well as the predicate function txy. So we can begin by saying, where it says every student, we go for all X as elements in the set S. Now we're just talking about every student, really verbatim, reading out what the symbols are saying here. Something happens after this, and here's our next quantifier, has taken at least one course. The at least one course part right here is going to be not a universal quantifier this time. At least one would be an existential quantifier. So we go exists Y in the set C of courses. And then we have to say such that student X has taken course Y. That's the predicate function way up here, txy. So throw that into the mix. Txy, and we've got it. That's the entire statement now quantified using the sets and the predicate function all at once. Any questions at all, folks, getting this statement down right here? Okay, now next we're going to go into for loops using pseudocode, and they're nested for loops because we have nested quantifiers. It's just going to directly match up with that. But it's a good idea to kind of step back from just this point and appreciate the spectacular complexity that's going on just right now on paper. We have an ordinary statement, every student has taken at least one course, but then we did a high level of abstraction using logical connectives, existential quantifiers, to take that whole statement and write it out here. We even needed a whole entire new mathematical function to make that happen. So that's a lot of work already, translating the whole statement into just logical notation. And now we're doing yet another layer of a translation. We're taking what we see logically here and trying to write down something machine code could really implement. I don't know what the coding system would be. It's going to possibly be databases, but if you're the high-level technical administrator working for ISU, you should be able to at least sketch out some pseudocode that can then be implemented with the correct syntax into any system that's being used. So that's what we're going to do right away. So imagine again, you will work for ISU as a technical administrator. Someone makes a claim, every student has taken at least one course, and you want to check it. Essentially, we're checking the truth of this statement right here. So let's write down what our goal is. We want to check if for all X and S exists Y and C such that txy, we want to check if this whole statement is true. So that would be the objective of the pseudocode that we're about to write out. So let's write this down here just to indicate what we're doing. So here will be the pseudocode on the left. On the far right, I'll just add some additional comments. I don't want my comments to get too kind of overwhelming, throwing it against the pseudocode, so I'm just going to separate them out in this way. So here's how we can start. We would probably want to begin with, well, we should begin with this quantifier right here. We want to check if every student has taken at least one course. Begin with the for loop involving every single student. So let's start by saying for X in S. And this would just be my style of writing this all out. If you used X element of S right over here, I mean, that would be okay. But usually for pseudocode, we're not trying to use any special symbols like this inclusion member of a set symbol right here. So we start for X and S. And at this point, it's a good idea to remind ourselves, what are we trying to do? We want to check if every student X, when we pair it with a course Y, we find that this flips to true at least once. That's the has taken at least one course. So we should initialize a Boolean value, a true false. Let's initialize it to false. And we also need a whole new variable at the same time. Let's define a new variable called taken course. I want to initialize taken course to false because we want to see if we can flip it to true by finding at least one course the student has taken, but initialize to false. So that would be my first step on that. And this stage, I can't do much with this for loop any longer because what I need to do is grab X, match it to every element of the set C, maybe every element, just depends, and check the predicate function to determine what its output is going to map to. At this point, we just need a whole other loop, so let's make that happen. So we grabbed an arbitrary student. We're going to be checking every single one of them for X and S, we just do the same thing here. And to make the structure a little bit logical, notice after I started a for loop, I indented to say this stuff is inside the scope of the for loop. But if they're nested, and we need another for loop because we have nested quantifiers, we should probably indent again, just for clarity of reading. So we'll go for Y in C. So now we're taking a look at all of the courses, but we're pairing with this X right here. So we do a check. We just want to see if this is true. And if it is true, we can redefine the value, take in course, flip it to true, and be on our way with that first iteration through the loop with student X, move to the next student, and just keep repeating until we've exhausted all students in S. So for Y and C, let's do this check. Let's say if, indenting again, T, XY, here we want to do a comparison, and usually in comparisons, we're not doing this right here where we're initializing a value for a new variable. Oftentimes in a comparison, you're doing something like this, a double equality. I'm not very picky at all on this kind of stuff, but it's good to kind of convey we're not re-expressing what T of XY is. We're just seeing if its value is going to turn into true. And if it does turn into true, we have found for the student X that that student has taken course Y. And we should just stop right here because why check the remaining courses in C? That would be wasted effort if it's already been flipped to true. So at this stage, let's just say taken course. We'll set this one now to true. But because of the if statement here, this will only happen if taken course evaluates to true. If it doesn't, no change right here. Taken course stays as the false assignment right here. So if taken course is true, we're done checking in Y. We should just leave this entire for loop. I mean, you don't have to, but for the sake of making the code run effectively, we don't, I mean, the set C could be tremendously big. And if we don't have to keep checking in C, because we already found the student has taken one course, we can say this statement, break. What that'll do is just take us out of this for loop right here, and then we're on to the next check for the next student. Well, any questions at the moment, folks? Or any changes you would make to the structure so far? We have a couple lines that we definitely need to add in to make this totally complete. Okay, well, taking a look at this again, let me double check my notes here so I don't lose my track. We took our arbitrary student in S. We're checking if it maps, or excuse me, if we compare X and Y to say the student has taken that course. If that comes out as true, we set taken course equal to true. Let me fix that right there and break out of this. But what if we grab a student X and taken course stays false when we go through here? In other words, TXY checking if it compares as true never happens. That means taken course stays as false. And we've answered this question. We would say, no, not every student has taken at least one course, because once we iterated through this loop right here, we could never flipped to true on that variable. If that's the case, this for loop right here should stop because we have found one student that has not taken at least one course. So let's say right out here, if taken course let me fix this again. There you go. So if taken course is now equal to false, actually, let's say it this way. We're not trying to reinitialize it as false. That would be really bad coding right there to make everything here in this inner loop essentially useless. We're just doing another comparison. We're going to say if taken course stays false, then we're entirely done with all the loops. So we can just go return false. We're not completely done with the syntax, but now what this is saying is we grab an arbitrary student from the set of all students, and if we check every single class in the set of all courses, and taken course still stays false and never flips to true, then the answer to this question, every student has taken a course, is false. So we should just break out of all for loops. I believe that's what this return would do. And just output for this entire syntax, false, as in we're going to say false to this statement right up here. So that's what I believe it would do by the pseudocode so far. We still are not totally complete with this. We need one more line. But any questions or comments or additions you would make? Okay, so now let's amend. Oh, sorry, go ahead. Yeah, that's the last thing we have to put just very down below. So last lines, and good thing for mentioning that because, you know, to be honest, I've written this out probably like 5 times before coming to class. It's amazing how much stuff you actually miss when you try to do this each and every time. So it's good to be really, really careful with this stuff. Other comments at the moment? Okay, so let's reimagine what's going on with this for loop again. We grab student X, we initialize taking course false, then we check every course in C. And let's imagine this time taking course flips to true, and it does it every time we go through the loop for every new X. That means this part never happens. So we would complete all the loops. Taken course would be set to true in this outcome. And so we should say for the overall statement here, return true, meaning if we never get this opportunity where taking course has flipped to false, this entire syntax, once we run it in whatever coding system it is, will just give us a Boolean true to say, yes, it is true by brute force checking, every student has taken at least one course. So that's what the syntax would look like for my kind of a hack job through it. I don't know if there's a clever way of writing this all out, but just for the sake of adding a couple more comments, let's spend a little bit more time with it. So again, this one we set to false initially. Here with the double equalities, this is just meant to be a check. If txy is actually itself mathematically, as in the mathematical function up here, to check if it really maps to a Boolean true. So that's what we're doing here. And that's why we have the double equalities. On this one, here we're saying if txy maps to true as a mathematical function, so one equality on this one, then we're setting taken course to true. Right here, this break line breaks out of the inner loop with the purpose of, if we found one course the student has taken, we don't need to check all of the other courses. We should just terminate that for loop right here, possibly saving a huge amount of runtime. Probably not. I mean, this is not the most involved database, but in a different setting with really large databases, this would matter. Then over here, the purpose of this is sets taken or checks, let me say that a better way, checks if taken course is false. And that's after running through this entire loop for one particular student X. And if it is, we will end all loops with return false. So this is kind of my idea on the right of why putting all this stuff in on the left, the order that it came in. And then this is the returning false. That means we're answering this whole question up here is false. But if we never hit that, last line is just saying return true as in answer yes to the overall question we were trying to take a look into. So we did it, folks. I think this is a tough problem. There is one like this in the homework. I'm not going to be picky when I go to grade these. I'll add comments and that kind of stuff, but just give it your best try. I understand that not everybody has taken a lot of coding. Some people may have taken very, very minimal amounts of coding whatsoever. And if that's you, don't worry about it. This is not going to make or break you in the course. Give it a try. I'll give you some comments on your homework, and you essentially are going to get almost all of the points for giving it your best effort. But I think this is our last thing to say in chapter 3 on logic. Any last questions or comments whatsoever with the pseudocode here? Okay, let's save this up. And now we're into chapter 4. We're not going to spend as much time in chapter 4. Our whole goal is to pick up a couple proof techniques before we go into the next proof chapter on induction proofs. So these are going to be some of the big techniques in the middle of the course before we get into the further on applications ending the semester. But let me double check that that's saved correctly. It's not stuff you necessarily want to redo. And here we are all the way in section 4.3. The reading says read section 4.1. That's just I believe, one-page blurb saying the importance of proofs as it relates to computer science. Then section 4.2 is a massive application on error correcting codes where the author does use proof techniques to show how all the methods work. I felt like that is rough before actually looking to the proof techniques, unless you've had a lot of coding. So we're jumping into section 4.3. So this will be where we start. As we do section 4.3, we're probably going to want to pull out your section 3.3 notes. There are a lot of gems in here that we need for proof techniques, proof writing. So we're going to screenshot them, insert them into the 4.3 notes, just for a quick reference. But if you have those notes open as well, they'll be very helpful. So here's how it all starts. A couple definitions, but really there's not a lot of definitions in this problem. There's way more examples, problems to solve than definitions. But definition 4.119 says, a proof of a proposition is a convincing argument that the proposition is true. And our author has a lot to say about this. His wording here about convincing is, convincing to who? That's the major thing. Writing a proof is like ordinary writing. And the argument you're trying to make is convincing to whoever the audience could be. So let's say it's right here. Who's the audience when you go to write these proofs? If the audience was people like the chair of the mathematics department, their proofs are probably going to be really, really terse, not a lot of information given. If your proofs are for someone like me, there might be a little bit more detail on there, but I'm not the audience either. When you go to write a proof, your audience should be this. The audience for your writing is fellow students in this class. So we want to write down an argument that can be understood by one of your fellow students. And what I'm trying to convey here is there has to be enough detail so that a fellow student in this class who's been following along all semester can take a look at what you did, even if they missed today, and get caught up of what we're doing. So that means there's going to be a good amount of detail here. You need to be really skeptical of everything you write. You have to be hypercritical of every connection, every statement you put down. But if you can do that, you have put down a highly convincing argument. And that's our whole objective here. Well, we're going to look into various proof techniques. But the first one is the so-called direct proof. Not a whole lot to say here, but the author does have some advice. A direct proof of a proposition, phi, starts from known facts and implications and repeatedly applies logical deduction to derive new facts, eventually leading to the conclusion phi. Kind of vague. Unless we actually do it, it's hard to say what the author is even talking about with the direct proof technique. But let's do it right away on example 1. Prove that the sum of any two even numbers is even. Kind of weird, right? I mean, there's a couple thoughts here. That's an even number. That's an even number. The sum is 20 and it's an even number, but that is not a proof. This is just one example. We need to check any combination of even numbers whatsoever and logically and soundly say the sum of those numbers being even has to once again be even again. How in the world are we going to do that? Well, we need some of our author says, known facts. This is about even numbers or the parity of a number being even versus odd. So here's some facts about even and oddness. Let's say it this way. Definitions. Let's highlight yellow to say we're just adding facts that we would need to know in order to really take on this problem and give a so-called convincing argument. And let's say it this way. If n in the set of z, I'm thinking integers because if we talk about even versus odd, we're only talking about the set of integers. So if n in z is odd, actually, let's go this way first. It's easier one to explain. If it is even, then there exists an integer k such that n equals 2k. This is the essence of being even. Essentially, what I'm saying here is being even means you can factor out a 2. Another way to say it is being even means your integer n was divisible by 2. And think about any even number whatsoever. It is automatically divisible by 2 as a feature of being even. So let's change this around and put down a new definition. If an integer n, or if n in z is odd, then, well, it's not even, but another way to say it is there exists an integer k in z such that, well, if n is equal to 2k, it's even. So what's our fix? The very next integer is odd, right? Increment by 1, and you've got an automatically guaranteed odd integer. Does that make sense to folks so far? Kind of weird. This is basically number theory in a certain sense, right? I think this claim is the one that's most sensible. The way to write down an integer as even is just that it's divisible by 2. That one's a little bit trickier, but let's just do a small thought experiment. Suppose you had an odd number, just any random odd number, 1139, that's an odd number. How can we write that out to really prove through this definition it's odd? Doesn't work to just look at it and say odd. That's the old way of doing things. But we want to do this in a very, very convincing way. So we're matching it up with the core definition right here. So we go and write, well, that's the key. If you can put out a +1, that's half the key rather. So let's take this 1139 and go 1138 +1. And I did this to myself. I think I'm going to need a calculator. Let me pause for just one moment. Okay, so this is half the battle of proving that your integer is really odd through this definition right here. Next thing is you have to take this part, 2k. We have to say once and for all that that integer right here is even. So let's see if it's really divisible by 2. I mean, we know it is, but let's do it anyway. 1138 divide by 2. We get 569. So back over here, we can say that this is equal to twice 569 +1. And then look at the format. We've got the 2 matching up with that 2. We have got the +1 matching up with the +1 there. And so this tells us, therefore, 1139 is odd. Pretty weird problem in a certain sense, but if you were trying to show 1139 is odd in this way, it serves a definite purpose, because if we're trying to prove this proposition as true once and for all as an airtight argument, you can't pick an integer. You have to work in full abstraction. Essentially, there's an existential quantifier here. There's a for all x, for all y. The sum of them is even. And that means we can't check every numbers. We have to work with the properties of being even or the properties of being odd. Well, we have the known facts right here. I'm not going to do a whole lot of crazy different mathematical facts. So we're mainly going to deal with issues of divisibility, issues with even and odd, issues with being rational versus unrational, and maybe an issue with a prime, but nothing too crazy, because for learning all this stuff, we don't want a whole bunch of heavy mathematics under it while we're trying to take on both topics. Okay, I think we're ready to get started on our first example. Any questions whatsoever, folks, before we try this out? Okay, one strategy that you could make here is take this statement, lean on what we did in chapter 3, and just re-express this with quantifiers. The sum of any two even numbers is even. Well, we're asking about two integers because we said even numbers. So let's say it this way. For all x in z, it says any two even numbers. So these are both universal quantifiers. Let's do the next one. For all y in z, we have a statement, x plus y, that's the sum of those integers, is even. So if we can really show this, we've got a proof. Let's get started. We'll put proof down below here.
Don't you have to specify there that x and y are even as well?
Oh, good point. I said just for all x and z, for all y and z, x plus y is even. Totally missing that part. Any two even integers. Let me throw that in there. Thanks for spotting that. This was going to be a weird proof without that information. Let's say it this way. X and y even implies x plus y even. And I think that's the actual statement we will be trying to check there. Does that look better with that fix?
Yeah.
Awesome. Thanks for mentioning that one there. And now, I mean, this informs how the proof should go. It's really just an implication in a certain sense. And now if we think back on what we did in logic, there's only one way to make this implication false. Implications are always really tricky, so let's take a look into that. So somewhere in here, we've got an implication. No, we don't. That's the other section, 3.2. Going all the way back into this section, it looks like. That's kind of exciting. And then way back in 3.2, I believe we have somewhere a truth table for the implication. There it is. I just wanted to highlight this right here to break it into the problem. Here's our truth table whenever any implication comes into play. Let's just insert that right there as a quick reference. And so now notice, the only way that this is ever false is if we assume P is true. Here's P right here. And we deduce from that that Q, and here's Q, is false. Well, we're trying to show this is true. So we would be avoiding these two. These are the vacuous truths. We're not going to start by saying P is false. We want to start by showing P itself is true. So we're really constrained on this line right here. We're going to start by assuming the hypothesis P is true. Then, working logically with our definitions above as well, show that the conclusion over here, Q, must follow, that it has to be true, and its truth followed from the truthness of P. So this is a great way to think about this anytime you notice an invocation. Let's start by assuming P is true, which just means assume X, Y are even integers. Saying even and integers is kind of redundant, but at least we're being highly specific now. The moment we said X and Y are even integers, we're right up here. This means there exists. Let's say it this way. Then, using some of the notation we have just right there by the red dot, let's say there exists K1 and the set Z of all integers such that X is even, so it's twice K1. I need a subscript on this, or we could just use a different variable K. K is not specific here, it could be anything. But I decided to keep it K just because we want to keep that definition in our mind with a role of K. And when we go to get the next quantifier, K1 is in scope of this whole argument, so we need a different subscript, go K2. So there exists K2 and Z, such that the second integer, Y, is twice K2. So that's all we've done. We've assumed P is true, and this is the logical consequence directly after making that assumption here. Any questions at all, folks, getting those two definitions down? Okay, now once we have this down for evenness, we're trying to show Q is true, and Q is the statement, X plus Y is even. That informs us what our immediate next step should be. We'll say here, next, X plus Y. Well, by substitutions, that's just going to be 2K1 plus 2K2 then, well, we're trying to show X plus Y is even. So that means we have to wrap back up to that definition again. We need to put something here. It's not going to be K any longer. It could be pretty involved, we're going to see in some of the problems. But if we can get something here, and if we can say that something is an integer, our work is done. It's really about that 2 factored out with some K value here as an integer left over. So come down over here. Not too bad. We could factor out a greatest common factor of 2. That leaves behind K1 plus K2. And that means our work is done. X plus Y is divisible by 2. It automatically applies it's even. So let's wrap this argument up and say, this shows X plus Y is even since this part's right here, K1 plus K2, is an element of the set of integers. Let me redo my color coding here. In other words, it wasn't K that we're saying is a set of integers, but it's a different K value. Any value here that's an integer asserts automatically X plus Y had to have been even. Our work is over at this point. All we need to do is signify the argument is over. And there's lots of ways to do that. I think a lot of people might typeset this. You might have seen this in a lot of places. Solid square like this is just a way to convey the argument is over. A lot of people might do this as well. This might be more common in computer science, I think. This is a way to signify end of the whole argument. Starts with proof, ends with a double slash, and now this is the entire self-contained argument. And other people who are feeling fancy might put in Q, E, D. This is mainly saying that you're probably mathematically trained and you're a working mathematician. This is Latin for quod erat demonstratum or something along that line. Sounds like an evil spell, but just means that for which has been demonstrated. Me personally, I can't draw a solid box too easily. QED seems pompous. I just go like this to signify end of argument. If you don't put anything down at all, that's not bad form either necessarily. I mean, the next problem signifies it well. But it's a good thing to consider if you're trying to say where your argument ends. It's good to begin by saying proof. Here's the start of my argument, and some special symbol to say this is the end of the entire discussion. Well, our claim was it was supposed to be a convincing argument, and how convincing it is really just kind of depends. There's a lot of elements going on here. Let's leave it up to the class. Any questions that you have about this argument? Anything that you feel like could be made more precise, or does this feel convincing?
Could you specify at the bottom that K1 plus K2 is divisible by 2 to show that it's even?
K1 plus K2 wouldn't necessarily have to be divisible by 2. All it has to be is a member of the set of integers right here. And save for oddness, K and Z could be anything. It could be either even or odd. But being odd just meant we have twice K plus 1. Being even just means we have twice K right here. So this one's a little bit weird with the K1 plus K2. It could be either even or odd, but it doesn't matter. X plus Y itself is even the moment we can separate 2 times any integer whatsoever. Does that
I guess that's what I
meant
is like, you're saying that K1 plus K2 is an integer right there, but you don't really point out that it's not being divided by 2 to show that it's even.
Right. Pretty much I was just trying to go back up to this structure, saying that K1 plus K2 and Z is just saying that we have found an integer in Z for which, as long as we put a 2 here and a 2 here, we have that's divisible by 2. But I think I see what you're saying as well. Let me know if I'm on a better track with this. I think what you're saying is this shows that it is divisible by 2, but then that asserts next, it has to be even if divisible by 2.
Yeah.
Is that what you're mentioning additionally?
Yeah.
Yeah, let's say that as well. That's a good clarification. Let's say here, let's see, X plus Y is twice K1 plus K2. This shows X plus Y is, let's make a modification, divisible by 2. Slight modification. There we go. Divisible by 2. Since K1 plus K2 is an element of Z. And then if we make that statement there, we can connect to the broader statement. Therefore, X plus Y is even as required. I put here as required this time just to mention that was our target, show X plus Y is even. So you didn't have to say X plus Y is even as required. If you left that off, that would be totally fine. But that's just a way to kind of redirect. That was our requirement to satisfy the proof. But yeah, I like that. Sorry, it took me a moment to understand what you were saying by there in the middle. Really, we could break this down into 2 topics. This is just showing divisibility by 2, and then implying even right after. Other questions at the moment, or inclusions or clarifications you'd like to discuss? Yeah, go ahead. You can, absolutely. But it's going to be a weird statement. If you have vacuous truth in your arguments, it means the original statement right here has a proposition P, which is just totally false from the very beginning. And if that happens, all you need to say is, well, the hypothesis is false. There's no way to force truth here. And that means the entire implication is true. So yes, that proof technique can come up. It's something that came up, let me see here. I believe somewhere in, maybe not section 3.2, maybe 3.3. Oh, maybe not that section either, maybe 3.4, but we don't want to spend too much time in there. It comes up with trying to show that the empty set is truly a subset of any other set. The vacuous truth, really the same structure, did come up in that case. It's a weird kind of proof technique because ordinarily you want to write out a statement that is true, but not by vacuousness. except certain things in mathematics, like the empty set, is just naturally coming up each and every time. So it's also unavoidable. But other questions or comments at the moment?
So would you be fine if we wrote X and Y are even or odd? Or do you want us to do like at the right under example one, where you kind of write out the statement, the P and Q part of the for the truth table? How you write X and Y are just even, is that fine? Or do you want us to be more like using mod 2 or something?
I would say this would be an okay assertment right here, but adding more detail like mod 2, that kind of stuff, that'd be more in the meat of your argument, like down here, where you probably would want to add that in. In fact, I would consider this whole statement right here really kind of optional. It was really just our sort of goal of taking another view of what is going on here logically so that we could attack it in the right way. And again, missing the P statement here when I first wrote it down was not good. That would have thrown us completely off on the proof technique. But yeah, this is a good thing to write in. I wouldn't say you have to be super specific right over here. Really, our high level specificity starts when we begin the proof argument down below, and anything above is just trying to help us organize our thoughts. But thank you for that question. Did that make sense there?
Yeah.
Awesome. Any other questions so far? These are really great questions, by the way. Yeah, absolutely. In fact, I probably want to take this as a screenshot and walk it down with this part here at least. Okay. Other questions at all, folks, so far? Let's try out the next one then. So example one says the sum of any two even numbers is even. And now example two says, prove that the product of any two odd numbers is odd. Really, it's the same kind of statement altogether, just slightly different scenario so we can get extra practice. These are not good problems to do one and done, in my opinion. It's a good idea to do at least a couple versions of these before we move on to the next. And that's pretty much what we're doing right here. Similar style of a question, and we're going to give a similar style of an argument. First, let's see how it reads out. Product of any two odd numbers is odd. So we're going to start with two integers, assert they're odd, and imply that implies, and say it implies this product of them are odd as well. Let's begin by quantifying. We have for all x and z, for all y and z. So here are the two integers. Here's the statement I missed on our first example. It says the product of any two odd numbers, so we should assert that right away. X times y is odd. And then that has to apply, or hang on, let me try again. X comma y is odd. I put in x times y, but I just wanted to say any two odd numbers, comma should have went in there. And now I want to write in xy odd means the product is odd. So it implies xy odd. Okay, got the quantified statement down. Kind of a struggle on getting this part here for me personally. I'm going to blame the mandatory work meeting. Kind of a cop out, but let's go with it. Does that look all right to folks as it stands? Okay, let's give a airtight argument of this then. First thing we want to do is work with the hypothesis. We're going to assume it's true immediately. So for right here where the red dot is, let's just say, assume x and y are odd. And it's really just kind of unfortunate. We can't even pick any specific odd numbers because the arguments we give have to work for every integer x, for every integer y that happen to be both odd at the same time. So this is highly restrictive with what we can do. We're working in full generality. X and Y, we often say, are completely arbitrary. Then, well, if X and Y are odd, we can say this means, coming back over here, there is going to be an integer k, so that 2k plus 1 is equal to n. So this is the essence of being odd. And let's come down here and say, if X and Y are odd, then there exists k1 in Z such that X is equal to 2k1. So now it's an even number. Add 1 and it's forced odd for the right and specific value of k1. Then do it again for Y. Exists k2 in Z such that Y is 2k2 plus 1. So now we have two odd integers, and even though X and Y are completely arbitrary, this is the way to write them in as odd integers themselves. Now we have a structure for which we can multiply X times Y and see if we can fit this once more to assert we have the product is odd. So let's go on to the next step and say, next, we have xy is equal to, make some substitutions, 2k1 plus 1 times 2k2 plus 1. Expand all of this out and we get 4k1 k2 plus 2k1 plus 2k2 plus 1. And now it's an algebraic mess, but if we work on this just right, we can find that integer k and the all-important plus 1. Plus 1's already there, right? And, well, the 2 is also part of this. We have to get 2 times k. Thank goodness then that there's a factor of 2 on every single one of these terms. It turns into this now. It's equal to 2 factored out of the first 3 terms, leaving behind 2k1 k2 plus k1 plus k2. And if k1 and k2 are integers, any arithmetic operation involving multiplications, additions, subtractions, still an integer. So there's our integer there, plus 1. That's just the leftover part after factoring. So once we have this, we can say, so I insert some space there. We can now say, finally, this shows xy is odd since we have found a value k right here that is in fact an integer. And there's more. We also have the plus 1, we have the 2, we have the entire right structure. The major takeaway is if it's really an integer right there, we're going to see some problems where that's sometimes kind of vague. But here it wasn't. We can say 2k1, k2 plus k1 plus k2 is an element of Z. And at this point, I would probably just end the whole argument. We worked through the technical definition of what it means to be odd 3 different ways: by redefining the variables, by multiplying out the product and showing it fits the structure. So at this point, I would say we've got an airtight argument. I think this would convince just about everyone, but I'll leave you to be the judge of that. Was this convincing, or was there certain parts we should take a closer look at? Might help if I zoom in a little bit more. Okay, well, we did it, folks. That's our second direct proof, as our author calls it. Really just another opportunity to practice these kinds of things. But there's a lot of other wild proof techniques we have to take a look into. There is proof by cases. Sometimes I can't just give one direct proof like this that works for any X and any Y. Sometimes it depends on the nature of X and Y. So we have proof by cases to handle that situation. Next one is going to be the proof by contrapositive. This is probably my second favorite proof technique. The idea is if this implication is true, well, It's logically equivalent to the contrapositive as well. And we'll pull that up from the notes just as a screenshot in here. This one, however, is my favorite proof technique ever because it's just so weird. It has a lot to hate about it. People call these non-constructive proofs. They're also called reductio ad absurdum proofs, Latin for reduction to the absurdity. But it's a wildly popular or powerful proof technique if done just right. It leaves a lot on the table, though. Proof like this leads to an algorithm, like the pseudocode we were just writing. But if I did a proof by contradiction on this, there is no algorithm. There's just a convincing argument that says the conclusion is forced to be true, but no steps to reproduce or implement a pseudocode to show how it's true, just that we know it is. So that's the downside of proof by contradiction. And then finally, last proof technique we'll look into is looking into counterexamples, which is, well, it's a proof technique, but we're trying to disprove something. We're proving the negation of the original claim, so it's a valid proof technique. But this is one that we've looked into a couple times, so this one is more just for the sake of putting everything in one spot. So that's the structure of the notes. I do want to take some time with these, because these problems, in my view, are not easy if you're seeing them from the very first time. So let's give this proof by cases a try and see where we end up. So idea with proof by cases is we have some proposition phi. This would be the proposition right here. We identify a set of cases and then prove two different types of fact. In every case we come up with, the proposition has to be true. And this is the easiest thing to miss. For all the cases we put down, every single one of them has to occur somehow, some way. So we have an exhaustive set of cases listing out all the potential possibilities, and one of them must occur. So those are the two things we're going to try to get through. And here's a proposition we want to show as true. For every integer n, the expression n squared plus n is even. If we quantify it, it looks like this. For all n and z, it didn't say what kind of integer, whether it's even or odd. It just says every integer, 0, 1,000,000, -12. But for every integer n and z, we have the statement. Here's the predicate, n squared plus n is even. And that's the entire statement we want to prove. A little bit more simple in this time. But it's complicated because if we just grab any integer n, we've got nothing to work with right here. How do we show n squared plus n is even? Our structure for showing that is this right here. And there's nothing I can do algebraically to n squared plus n to get it into this format, 2k. So it feels as though we're stuck. But not really. We still have some tools that we can work with. So let's start working out this proof. This is a non-standard proof technique. The other ones were the standard ones, the direct proofs. For using something specific, that's a good call to just alert to the audience, what are you doing? How are you attacking this problem? And we're doing a proof by cases. So we need to write down an exhaustive list of cases so that every possibility for the integer n that can occur will occur. Let's go case 1. And here's where the ingenuity comes in. It's not always clear what the cases should even be. But if you decide to do proof by cases, it means you saw some insight into this problem. The insight might be that if you're trying to conclude n squared plus n is even, then you're operating on n by determining or deciding is n itself even or odd. If you make those kinds of thoughts, you're arguing by cases, and that's what indicates this should be a proof by case. So let's say for case 1, n is even. Now we have something we can work with. If n is even, we can use this structure right here to write down something algebraically. Feed it back into the expression n squared plus n. See if we can do factoring just right, and if we can, we've shown n squared plus n is even. But this is only half of the cases. We have to discuss n is even, then we go to the next case, discuss n is odd. But notice If those are our cases, every one of those cases has to occur for every integer n, because for every integer n, it's either even or odd. No middle ground on that. So let's start off with a n being even. We can say right away, this means for even, there exists an integer k in Z such that n equals 2k. So that's the essence of being even. Now, our goal here is to show n squared plus n is even. So let's say just write in next. N squared plus n becomes, by substitution through this 2k squared plus 2k. Do a little bit of algebra, and we have 4k squared plus 2k. And now we're trying to force in that integer k right here, which is doable only because both of the terms are divisible by 2 now. So that means we can factor out 2, leaving behind 2k squared plus k. We've now found the integer 2 on the outside. If k was an integer from the beginning, so is 2k squared plus k, so that's an integer as well. And this is enough to show that n squared plus n is divisible by 2. Let's jump to the larger conclusion. It also shows n squared plus n is also even outright. So let's say it here. And so n squared plus n is even as required. Again, the as required statement, not totally required there, but it's really just a way to tie in. We looked here and we made the right conclusion. Now we just do it all over again, because if it's a proof by cases, we need an exhaustive list of cases. So we go down immediately to case 2. And in case 2, we say n is odd. Well, if n is odd, we go back up here and just write out the essence of being oddness. This means there exists a new k value, but this is proof by cases. This k value was only in the scope of case 1. We can just say k again, and this k is only in the scope of our whole argument in case 2. This time, no conflict in notation. But if you did go k1, k2, still no conflict in notation, it's just not necessary this time. So let's say there exists an integer k, exists k in Z, such that n, because it's odd, is now equal to 2k plus 1. So we've got a k value there. We need a 2 here and a plus 1. We can make all that happen. For n squared plus n, our work is done. But notice the direct parallelism here. Oftentimes, if you're doing a proof by cases, and if you felt like your first argument worked out, try to mirror it as much as possible, even in the penmanship, the width of how you're writing out, because all it's doing then is helping you read your proof again to see if you did everything just right. If I try to make it as parallel as possible and I make a mistake, it's going to stick out a lot, and we'll be able to correct it. Okay, so let's say right away, following the argument above, next, working with this, n squared plus n, we need to show it's even still with n odd. So we take this right here, substitute it inside, 2k plus 1 squared plus 2k plus 1. And let me see if I can just steal that again. Okay, so finally, after we have this, do a little bit of algebra, expand what we have here by the red dot. We'll get 4k squared plus 4k plus 1, and then plus 2k plus 1. We have like terms we can combine. We have altogether 4k squared plus 6k plus 1 plus 1. It looks silly, but remember, we always want to keep our eyes on the target. We're trying to match up this structure right here. So that +1 should just be left alone. And we're trying to get a 2 factored out as our next step. Hang on. No, we're not trying to show odd at all, are we? Sorry, go ahead. Yeah, I got mixed up on what we're trying to show. I should have been looking up here. We're going for even. And thank goodness, right? Because it looks like there is no way to actually write this as an odd whatsoever. I was going to try to take this and factor out a 2. That's not going to happen at all on this thing. And so that tells us no way could it be odd. Thanks for spotting that. So let's actually combine our like terms. Let me throw a line through here so it's not a distraction. We're matching up that structure. So we really want to combine the like terms. Here's the +2, which then finally allows us to factor out a 2, leaving behind 2k squared plus 3k plus 1. So here's the 2 that we needed, the all-important 2. The not as important, but still fairly important bit is this. It has to be an integer. But if k was an integer, all of this is forced to be an integer as well. Really, the only time you have trouble here is if you had something like 2k squared over k minus 3. Now we've got a problem because that may or may not be an integer, may not even be a rational number, it could just be undefined entirely. This is actually going to come up somewhere in the notes. But we can now just say, we got here, this shows, let's say it's slightly different, and so n squared plus n is even as required. At this point, we can end the argument. This was a weird one to get sidetracked on, but that's a kind of nice thing about looking at these really, really careful. We could tell right away it just wasn't even going to work out, even if we force it to argue that it's odd. Well, there's the entire argument altogether. We showed for every integer n squared plus n is even. And to me, this looks like a convincing argument, but it may not convince everyone. Anything extra that folks would like to throw in here to make it totally convincing? If we all feel good about this, then I would agree with you. I think that some people might say, however, let's add just one more statement here before we totally finish this off. The one thing that you might have felt like wasn't quite there, I think it's a bona fide concern. It's not a quibble. It's that statement. We developed cases, and the statement phi that n squared plus n is even was true in every single case. But it might have been a good idea to mention that one of those cases has to occur for every integer n. That's what part 2 is mentioning down here. So in this problem, I think a lot of people felt like it was obvious one of these cases has to occur. But in a more complicated proof, it might be non-obvious. So this is a good last statement to write in. Or every n in Z and is either even or odd. So here I'm saying these are the only 2 possibilities for n, and n squared plus n is even in every case. So I would say this is pretty optional on this one, but it's a good thing to pay attention to. If you ended the argument here, it would have still been for full credit. Well, that's too far of a zoom out. But at least what we did here was we attacked on that part. One of the cases has to occur was the whole purpose of putting this in. What we did, folks, for every integer n, it turns out n squared plus n is even. These are strange facts, right? But at least we're using them only for the purpose of looking into the proof techniques. We're not trying to throw in a really, really complicated statement to lose sight of what we're trying to really just demonstrate, the proof techniques themselves. But for the next one, this will be proof as cases as well. Let's give this one a try. Well, I don't know if I can finish this in 5 minutes. But we can still set this one up. Proof by cases. Why do we need proof by cases? Well, we have something quantified that goes for all X and R. It's the statement that X itself is less than or equal to the absolute value of X. And I think that's a pretty convincing statement, but we need to say exactly why that has to be true. I claim that this is a proof by cases, and the reason for this one is not so much the ordinary statement here, it's more just because of the absolute value function itself occurring. The absolute value function itself occurring, well, how would you define this? Lots of ways. One way you could write out is absolute value of X is the square root of X squared, but it doesn't really help us here, sadly. Another way you could write it, more helpfully, is that the absolute value of X is a piecewise function, which just means it's defined case by case. We're dealing with a piecewise function defined case by case, and we have an argument involving it. It's naturally a proof by cases problem itself. So absolute value of X is defined to be X. In the case of, we just usually say if, but let's say it this way, absolute value of X is X in the case that X is greater than or equal to 0. And absolute value of X is the opposite of X in the case that X is strictly less than 0. Or you could say less than or equals here, less than or equal to 0 here as well. It would just feel like there's redundancies, but it would still be the right, exact right function. So this naturally leads to cases. Case 1, we're going to say, assume X greater than or equal to 0, just coming from the first branch of the piecewise function. And I forgot the number. Let me say it this way. Case 1, assume X is non-negative. Case 2, assume X is less than 0. And from both of these assumptions, we can write out an argument that'll look slightly different because of the values of X, but we'll be able to write an argument that's going to lead to the conclusion X is less than or equal to the absolute value of itself. But really the major reason to put in this problem again is if you have a piecewise function, you're automatically doing proof by cases. Well, not automatically, but an indication it might be a great technique. We'll have to tackle all this when we come back next class, but yeah, question first.
Obvious, but in proof by contradiction, you're assuming, the opposite.
Yeah.
Trying to find something that we know is false so that we can say it's true. That's kind of half of what we're doing here. So I guess what I didn't quite catch is when would you do contradiction and when would you do cases to have that extra step there?
Gotcha. A really good one for proof by contradiction would be show root root 2 is irrational. This one is kind of like the prototypical example of proof by contradiction, because a direct proof of this, wildly hard. It's not something that we could approach whatsoever. That's a hard constructive proof to show irrationality. But we could show this by assuming root 2 is rational. We'll do a bunch of algebra and we'll directly lead right away into a contradiction. We'll say the reason we hit a contradiction was this assumption right here. It's false, which then flips it to the original conclusion up here. It's irrational. This one's going a little bit different. Here we're saying X less than or equal to X, but we're never negating this condition right here. We're leaving it stand on each one of our conclusions. We'll end by saying this shows X is less than or equal to the absolute value of itself. So that's the difference on what's going on with this function here by cases.
Oh, I see. Yeah, it isn't a negation. You're just kind of splitting it into two.
Yeah, exactly. Okay. We're splitting the domain of X's and R's into two different domains, essentially, for now two different arguments. Other questions at the moment? Thanks for that question. That is an excellent clarifying question between this here and what's coming up next below. But others at the moment?
This is unrelated to the topics we're discussing, but after class, may I ask you about a homework question from 3.4, Professor?
Absolutely. I'll be very happy to help out.
Thank you.
Well, looks like we're basically out of questions, but if you do have others, like Michael mentioned, feel free to stick around. My next class is at 7:30, so I'm just sort of meditating here. But have a great night, folks. When we come back on next week, Monday, we'll work through these problems as well. I don't think we're going to try to finish it on Monday. There's no reason to race through this stuff. So it's probably getting completed when we come back a week away from today. But have a great night, folks. Have a great weekend. And let me save this up real quick. We'll take a look into that question.
Thank you very
Which
much.
question it was?
So I was looking at question 12.
Gotcha. So was it, I forgot already,
3.4.
3.34, gotcha. 3.4 and into question number 12.
Yes, sir.
If someone is a comedian, then they tell jokes. Interesting. Yeah, go ahead.
So,
All comedians tell jokes.
Oh.
Yeah, absolutely. Yeah, go ahead.
so for that question, I was reading the if someone, and I wasn't sure. I read it initially as an existential operator for someone, but after I thought about it a little bit, I realized it could possibly be universal if you read it a certain way. So I wasn't sure if it was like number 9 where it was universal or if it was just solely existential for number 12.
Gotcha. So let's see here. If someone is a comedian, then they tell jokes. Versus all comedians tell jokes. Yeah, I see what you mean. They look like very, very similar questions on this one. So for all comedians tell jokes, it says C of X, X is a comedian, T of X, X tell jokes, right? Symbolically using quantifiers. So because we want a quantifier on this one, I'm going to try number 9 first only because it looks like the easier one to compare against. I'd probably go on this one for all X. Now, X is just going to be a living person. So if we wanted, we could have a universe, all living people. Let's actually do that. U is all living people. So we could say next for all X in U, X is a comedian, is C of X, T of X is X tells jokes. So I believe this one should be the implication. C of X, if you're a comedian, then T of X, you tell jokes. So that's my first thought on this one in number 9. Does that make sense to folks for this write out?
Yes, sir.
Okay. And then now I see the question that you're asking. This one, which feels very similar. If someone is a comedian, then they tell jokes. Yeah, my first thought, let me just write it down. My first thought was also, is this existential? Someone, I'm thinking there exists an X such that is a comedian, C of X, which implies they tell jokes, T of X. But I would have to think about that. How do folks feel about that? Do you have an argument for a different way to visualize this one? Yeah.
I would argue instead it's the converse. So like you could say 9 as like if someone is telling a joke and they're a comedian, that's the way I would look at it at least.
By converse, you mean switching the order of the arrow right here?
I believe so.
Gotcha. So someone is a comedian, then they tell jokes. Yeah, usually with the converse, they would have to have, if someone tells jokes, then they're a comedian to really flip that arrow around. You know, at this point, I'm going to use my cheat sheet here. Let me see what I did when I wrote this out the first time. It might be exactly the same. Let me see here. When I did number 14, I wrote number 12. Thank you. I put it for all X. For all X, C of X implies T of X on that one.
I was working with Michael on this as well, so we kind of had the same question, and that's how I thought it should be wrote, was the for all, because it's saying if someone out of our universe, which is all living people, so if they're a comedian, then they tell jokes.
I'm kind of on track with that as well. I'm reading it first as an existential, but more thought. I think that's what I put down on paper as well on this one. Yeah, it seems like a for all, which means doesn't seem like it's saying anything different than number 9, kind of a redundant problem in a way. But as awful as it is, looks like a pretty good problem in the sense that it's forcing us to tell if there's a difference between the two. You know, I'm gonna have to take another really quick look at this to see if I can really discern a difference. I'll report back to this one to the class if we come back on Monday for just another look into that one. Because I'm also just sort of surprised that I would write down a homework set with 2 questions that looked almost identical. That is on its own pretty weird. So thanks for mentioning that one, folks. I'll take another look at that and bring back a report on it on our Monday's class. So be a reminder. And that's our discussion right there. My first thought though, well, no, my second thought is still, it looks like it's a for all is where I would probably bet on if I had to bet on it. But other questions at the moment, folks, before we call tonight?
Yeah, do you have time for one more on 3.5?
Yes, possibly. I've got to start turning over to setting up the next class in just a couple minutes, but let's take a look at it. Thank you. So 3.5 next. Thank
And it
you.
was number 5.
Gotcha. 5 on 3.5. The product of any 2 odd integers is odd. Hey, that kind of feels
So
similar to what we were working today. Yeah, go
yeah,
ahead.
it's less of a question about like how to do it, but more if you could do it this way. So like in
Gotcha.
your quantifiers, you would obviously do for all x that's contained in the integers. And then could you do like how you do greater than or equal to 0 in some cases? Could you do mod 2 equals 1 on the z to
Yeah,
specify that they're odd?
absolutely. That'd be totally fine. Yeah. So
Nick.
you said for Z, for all Z in
Or
Z?
z
Is
as
that
an
what you
integer is my fault.
Oh, gotcha. So,
So kind of similar. So when you're specifying that it's positive, right? You would write z and then to the power of greater than
oh, I
0.
gotcha.
Yeah.
So saying all X and Z bigger than 0 for positive, but you want to say X is odd automatically. So mod 2 equals 1 on Z is what you're saying.
Yes.
It's descriptive. Yeah, that would work out. That's automatically asserting all in one. You're starting out with odd integers. So yeah,
Okay.
I like that notation. And it's in the spirit of what the author was doing all along in the book as well.
Sweet.
That makes it so much easier.
Well, thanks for the questions, folks. I got to now turn over to the next adventure, Calculus 2.
Have
But
fun.
have a great night. Thanks. We definitely will. Thanks. Hello, folks.